good, everybody? I'm Professor Jennifer Hill, and I run Divide and Conquer Math, which is a YouTube channel and website dedicated to helping you learn math on your terms. So this video is part of my Study with a Math Professor series, so I always like to just give a little bit of an introduction. So this series is specifically on derivatives, so this is really here to help you get prepared for a calculus test on derivatives. So in this series, I have 4 videos starting with kind of basic problems, medium level of difficulty, pretty difficult problems, and then kind of mixed levels. So the reason that I have this kind of set up in this structure is that kind of twofold. For one thing, this came out of requests from my students wishing that we had more time to go through review. And just with the way that the scheduling works, at least at my school, the schedule is just so packed, I usually don't have time for review. So I wanted to make these videos to help my students kind of answer any questions and do extra practice, and they can kind of work still alongside me. The other thing about these types of videos is that they really align with my studying philosophy, which if you've never heard that before, you can look in the description below. I've got a whole video on how to study, just kind of some guidelines on what works and what doesn't. And really I can summarize it as practice, practice, practice. And you really want to start by laying a foundation and making sure that you're super solid on some of the basic problems before you start working your way up. So you're going to want the problem set for this video, and you can get the problem set by looking in the description below. And the way that these videos work is the first hour you will see me working on my own stuff. So I'll either be writing out notes or doing slides or whatever, and you'll basically have like an hour of work time, and that timer is really just there if you have trouble getting motivated to start studying. Just think of that as a way to help motivate you, and that's like a 1 hour time that you know you are dedicated to working on this. Now, the problem set, you want to work through as many problems as you can. You might not finish them all in an hour, and there's nothing wrong with that. If you need more time, you can always just start the timer over or pause the video or whatever you need to do, no problem. And you can also check all of your answers by looking in the answer key, which is also in the problem set. Now, this video, I am not giving you instruction because we just have so many problems to go through, but what I do have in that problem set is also suggestions of videos to go and watch if you feel like you need a refresher of instructions or examples or whatever. So we've got you covered for everything that you might need between really that set of problems and then this video. Now, if you realize that you didn't get a problem right and you want to see the solution, then I have time markers in the description of this video so that you could just fast forward to any solutions that you want to see. So hopefully, you know, if you go through this whole series, you feel like you're pretty prepared for a calculus test on derivatives. And of course, modify the problem sets to your needs. So if there's something that's not actually covered in your class, consider, you know, just not doing that problem, but I made these problem sets to cater to kind of how my class works. Okay guys, so let's get started. Hey guys, I'm going to start going through the answers. So if you're not done, you can hit pause here. You can always restart the study time or do whatever you need to do, but we're going to get started. So for these first set of problems, we want to use the definition of the derivative or the alternative formula. And so just for your reference, these are those two formulas. So if you don't know them, maybe you want to pause and just write them down. So starting with the first problem, so I want to use one of those two definitions or formulas to find the derivative of this. So that is what we are being asked. It is not just take the derivative using whatever you want. We are being told to do this in a specific way. So it really doesn't matter which one of these two rules that you want to use. I think in this case they're actually probably about the same in terms of difficulty. So I think I'll use this one here, the original definition. So what I'm going to do is just to really show you like a good practice to be in. When you take a test, you want to write out the formula that you're trying to use, because that really indicates then that you have a plan and you know what you want to do. So if something goes wrong from here, but I got this first part right, at least it was like very clear what I wanted to do. So now from here, so let me first evaluate this part in pink, and then I'll do this part in green. So I'm going to color code this. So this will be the limit as h approaches 0 of 3 times x plus h minus 1, and then minus, let's see, minus, and then put this in parentheses, 3x minus 1, all of this divided by h. Okay, now from here, you really just want to sort out kind of all the algebra, so I will show you this in all the detail. So this will be 3x plus 3h minus 1 minus 3x plus 1 over h, and then these drop out and these drop out. So you're really just left with 3h over h, so that just becomes 3, right? So I've got the limit as h approaches 0 of just 3, and so that limit, the limit of any constant, is just that constant, so this is going to be 3. And if you realize now that you need more practice with that, then I would recommend that you look up problems on the definition of the derivative. You can look at the description of this video, and I actually have a link to a video on more problems like that. Okay, so for number 2 here, so the directions are still that you have to use either the definition of the derivative or the alternative formula. So I've got those two just written here if you need to write those down. So to show you how to do this then, once again, I don't know that it necessarily matters in this case which formula that you want to use. So I'm going to go ahead and just use the original. Actually, I'm going to use the alternative formula. I think that might be a little bit faster. So you should get the same answer either way, but just to kind of play around with this a little bit. So I've got the limit as z approaches x of f of x minus f of z over x minus z. So like I've said, you always want to write down the formula that you're planning to use, because then it makes it very clear on an exam what your game plan is. So if something wrong happens after this, it was at least clear that you kind of knew what you wanted to do. So now I need to just plug in f of x and f of z. So let's see, I've got the limit as z approaches x of x squared plus 5, and then minus z squared plus 5. So there are the two functions, all of that over x minus z. Okay, so now in simplifying this, so in this case I actually think that this formula might be a little faster than the other one. So notice that the 5's drop out. So what I'm left with then is, let's see, I've got this x squared minus z squared over x minus z, and you can see that you can factor the top. So if I factor the top, so I'm going to have x minus c, x plus z, so it's just the difference of squares, over x minus c. And now I can see, right, that the x minus c's cancel out. So now I've got the limit as z approaches x of x plus z. Okay, so now I can take the limit, which would mean that I will just plug in x for the z, so I have x plus x, so that equals 2x. And so then just by eyeballing this, if you know your derivative rules, which I assume you do by this point if you're watching this video, that's definitely the derivative, so we know we found the right derivative. So I always do that like last minute gut check of just checking your derivative. And so these problems are really referring to like the definition of the derivative or the alternative definition, which is what I use. So if you're looking to practice more with that, you can look those up. And also just something I want to point out before I move on. Notice the consistency in my limit notation. So I wrote limit the entire way down until I actually evaluated the limit. And then once I actually plugged in that x, then I dropped the limit notation. So just make sure that you're being really careful with that, because that's the type of thing that can really ding you on a test. All right, so for number 3 here, so we still have to use the definition of the derivative. So I can use either one of these definitions for this particular problem. And I will tell you, so if I have a choice, so I would actually not want to use this definition, because what will end up happening is that I would have to take x plus h to the third, and that's just a lot of multiplication. So I'm going to do this one using the alternative formula. I have videos where I compare these two formulas, so if you want to just see how they kind of shake out, you can check those out. But for the purpose of this video, so I just have to show you one of these ways to do it. So I'm going to use, oops, let me grab the white pen. I'm going to use the alternative definition. And so once again, so you want to write down the whole thing, the whole formula before you start, because it makes it very clear what you're trying to do. And now from here, I just need to plug everything in. Oops, and this is z is going to x. Okay. So this will be x cubed now minus z cubed over x minus c. And so the only thing with this is that you have to remember the difference of cubes formula, which is something that you should really know in a calculus class. So the way that the top is going to factor, that's x minus c, x squared plus xz plus z squared, all of this over x minus c. So that's that's the way that that's going to factor. So like I said, if you were like, oh, I have no idea, this is just like a formula. So it's the sum or difference of cubes. So you can just quickly look that up if you forgot that. And like I said, that's something that you probably do want to have memorized for a calc class. All right, so anyways, so now obviously these will cancel out. So now I'm left with the limit as z approaches x of x squared plus xz plus z squared. So now I can basically just plug in x's where I had z's. So this comes out to x squared plus x squared plus x squared. So I get 3x squared, which I know the derivative, just looking at this is going to be 3x squared. So now I know I found the right derivative. So we're good to go. And if you're looking for more problems like this, you can look up the definition of the derivative. That's kind of what this is working on. So for the next set of problems, we just need to take the derivative, and we can just use our derivative rules. So this first one, oops, let me switch my pen color again. So this one is really just using the power rule most of the time. So I'm going to bring down the 5, so 5 times 4, this is going to be 20x to the 4th minus 12x cubed plus 6x squared plus 16x minus 3. So this is a pretty straightforward derivative problem. So if you didn't get that one or you need to brush up, I'd highly recommend checking out some of just your basic derivative rules, because this one's pretty basic as far as those rules go. So moving on to 5 here. So this one is also just really using your basic exponent rules, but you have to think about this now in the right way. So one thing that I like to do with problems like this is I rewrite them. So instead of having them in this fractional form, I think of this as 5x to the negative 1 and 6x to the negative 2nd, because then that just makes it easier for me to use the power rule. So if I take the derivative of this, this is going to be negative 5x. So I subtract 1 from the exponents. This will be now negative 5x to the negative 2nd, and then minus 12x to the negative 3rd. So remember, you're subtracting 1 from the exponent. Now, depending on the final format, I would say that what we wrote down is fine. Some teachers or some systems will want you to rewrite it in its fractional form. If you're in my class, this is like potato, potato to me. It doesn't matter which form you have this in. Okay, so moving on to 6 here. So this is another application really of just the power rule. So what I want to do before I start this is I want to rewrite this expression just in all exponents, because I think it makes it easier to take the derivative when I have that visual. So this is 5 to the 4th, 3x to the 1/3. So this is x to the 1/2. And then I can't really rewrite this any other way, right? This x to the 3 pi. So keep in mind, this is technically a number. So when you see an exponent like this, it's really there to get you off your game. The point of throwing something weird in the exponent is to really make you think for a second. But really, like when it comes to derivatives, it's just, is this a number or not? So if this were an x, this would be a different problem. But this is just a number. So you're still just going to use the good old power rule. So let's see, if I start this, so I bring down the exponents, this will be 5/4 x. So I subtract 1 from that, that'll give me 1/4. And then let's see, this will be 3 times 1/3 x to the negative 2/3. And then this will be 5 times 1/2 x to the negative 1/2. And then this will be 3 pi, so I still bring that exponent down, x to the 3 pi minus 1. So I'm kind of running out of room here, but now let me just simplify all of this. So I get 5/4x to the 1/4 minus x to the negative 2/3 plus 5/2x to the negative 1/2 plus 3 pi x to the 3 pi minus 1. Now I know that this exponent looks really goofy, but like I said, this is ultimately a number. And unless I start getting into like a decimal calculation, which I really don't think is necessary here, this gets the job done, right? And just one other note here. So to me, this is fine. Some teachers might want you to rewrite this with no negative exponents, so then you would have to rewrite those two exponents. So just a heads up on that. And this type of problem really just has to do with the power rule. So if you're looking for more problems like that, you can just look up the power rule. Okay, so moving on to number 7 here. So for 7, we've got 5x times e to the x. And so I just want to show you, this is my little cheat sheet of some of these derivative rules. So I have here the product rule and also the derivative for the natural exponential. So if you forgot this and you want to pause the video, you can write these down. So what I need to do here is first I need to just think about what are the two functions I have. So I've got 5x, and then I've got e to the x. Okay, so to take the derivative, I need to take the derivative of 5x, and the derivative of 5x is just 5, and I leave e to the x alone, and then I add to that, so I leave 5x alone now, and I take the derivative of e to the x, which is just e to the x. So this is it. This is actually the whole derivative. So if you want to go and practice that some more, you can try the product rule. Okay, so for number 8 here, I have just a bunch of trig functions. So sine x minus tangent of x plus cosecant x. This is a great one to check if you know your trig functions. So here's just a quick cheat sheet if you are not as familiar with some of your derivative rules. So this is really what I'm going to be using to finish this problem. So you can pause and write this down if you need to. So for this one then, let's see. We've got y prime is going to be cosine x minus secant squared x minus cosecant x cotangent x, and that's it. So this is really just one of your basic trig derivatives, so if you want to practice more like that, that's what you can look up. So moving on to 9 here. So for this one, I need to use both the product rule, so I'll just flash that rule up here if you need to take a look at it. And also I'm going to need my trig derivative rules, so I've got all those listed. Again, you can pause if you need those. So to take the derivative here, so I have really two functions, e to the x and cosecant x. So as I take the derivative, first I want to take the derivative of e to the x, which is just e to the x, right? And then I do nothing to cosecant x. And then I add to that, I leave e to the x alone, and I take the derivative of cosecant x. So that's going to be negative cosecant x cotangent x. And so then I just want to rewrite this and make this just look a little nicer, I guess. So I've got e to the x cosecant x minus e to the x cosecant x cotangent x. So this really falls like into your trig derivatives. So that's what you can look up if you want to practice more. So for 10 here, I've got y equals 4x squared minus 3x over sine x. So for this one, we're going to need both the quotient rules. So I'll just pop up that little cheat sheet. So here's our quotient rules. Again, you can pause if you need that. And we need to know our trig derivatives. So there's just the list of those. So for this, the top part is going to be my f of x, and the bottom part is going to be my g of x. So the way that the quotient rule works then is first I take the derivative of the top function. So the derivative of 4x squared minus 3x is going to be 8x minus 3, and I multiply that by the bottom function sine x. And then I subtract this. I leave the top function alone, and I multiply that by the derivative of the bottom function, which is going to be cosine of x. And then I divide all of that by the bottom function squared. So I've got sine x squared. Now, as far as like simplifying this goes, this is a little bit like a matter of preference in some ways. There's not a lot of simplification that you can really do to this. So if you were to distribute these out, it's not like you're going to be able to combine any like terms because these are connected to sine x and these are connected to cosine x. So I think this is really as far as we can go with this one, though some teachers might want you to, distribute or whatever. But we can't cancel out like the sine of x and the sine of x here. That wouldn't work because there's no sine of x here. So that would be an illegal cancellation. So I just wanted to point that out. And so if you're interested in looking at more problems like that, you can look up trig rules or quotient rules. That's the type of problem that is. Okay, so for number 11, I've got tangent x cosine x. So just very quickly, just to show you, so I'm going to need the product rule, which is right here. And I'm also going to need to know my trig derivatives. So here's the list here if you need to pause either one of those. So for this one, tangent x is going to be my first function. Cosine of x will be my second function. So I take the derivative of tangent x, which is secant squared x, and I leave the second function alone. And then I leave the tangent function alone, but I multiply that by the derivative of cosine x, which is negative sine of x. And so really the only thing that you can do to simplify this is now maybe just bring this negative out in front. There's really not any other meaningful simplification you can do in this one. So I've got secant squared x cosine x minus tangent x sine of x, and we're done. And this really falls kind of under the category of your standard trig derivatives. Okay, so for number 12 here, so this one is a little bit interesting. So we've got 4x plus 1 times 3x squared plus 2. So here's the thing. There's more than one way that you can do this. You could use the product rule here, or in looking at this, you could just go ahead and multiply everything together. So sometimes when you're working through these derivative problems, there's a little extra work you have to do. Personally, I think it would be better to just go ahead and kind of FOIL everything out. So this becomes 12x cubed plus 8x plus 3x squared plus 2. I would much rather take that derivative than use the product rule. So now if I take the derivative, I get 36x squared plus, let's see, 6x plus 8. So notice I just also reordered this into descending order. So there's your derivative there. So if you're looking to practice more problems like this, I would say this kind of falls under your more like basic derivative rules, but it is a little bit tricky. So if you're looking to practice more like that, you can look up problems like that and you'll probably find other ones that look like this. Okay, so for number 13, I have tangent of x over e to the x plus 4x squared. So this is really just using the quotient rule. So let's see, I'm going to need my natural exponential, my quotient rule. I'm also going to need to know my trig derivatives. So if you need to pause any of those to read those over, feel free to. So for this one, to take the derivative, let's see, I'm going to take the derivative of the top function, which is secant squared x, and I leave the bottom function alone, like this. And then I subtract off, let's see, I leave the top function alone, so tangent x,
and I multiply that by the derivative of the bottom function, which will be e to the x plus 8x. I'm running out of room here. And all of this will get divided by the denominator squared. Okay, and so now just the other thing I want to kind of point out here, so this is really as far as you can go with this. You really can't like clean it up too much in some ways, but if you did want to try to simplify this a little bit farther, what you could do is you could break this into two parts. So what I mean is I'm going to have secant squared x times e to the x plus 4x squared, all of that over that denominator, and then I'll have the other part of this tangent x and then e to the x plus 8x over the same denominator. So some books or teachers or whatever, they might want you to simplify a little bit farther, so I wanted to take this just one possible step farther. And so then you can see I can cancel out this factor with one of these factors here. And so then let me give myself a little space. Okay, so a potential final way to write your answer would be secant squared x over e to the x plus 4x squared minus, maybe I'll put this in front, e to the x plus 8x tangent x over e to the x plus 4x squared squared. Okay, so for 14 here, so now what I'm going to do is I'm going to use the quotient rule, and I need to know all my trig derivatives. So just to quickly flash those to you, there's your quotient rule. It's at the bottom here, and then here's my list of trig derivatives. So for this one, what I'm going to do is I'm going to use my quotient rule. So first I take the derivative of the top function. So the derivative of cosine is negative sine, and I multiply that by the bottom function, and then I subtract off. I leave the top function alone, and I take the derivative of the bottom function, which will be negative cosecant squared x. And then all of this is going to be over cotangent squared x. So I square the bottom function. Okay, so as far as like simplifying this, so I guess you have kind of some options here. If you wanted to break this up into two different parts, so what you could do is you could call this negative sine x cotangent x over cotangent squared x, and then I've got the other function, so this actually becomes a plus sign. So I have cosine x cosecant squared x over cotangent squared x. So in separating this, what I get is that I can cancel out this cotangent with one of these. And then maybe I'll just have the thing that's negative, so this is a negative sign here, I'll just have that come last. So just kind of making the answer look prettier, I guess. In math, we usually like to have the negative sign come second, just to make it look nicer. I don't know why we think that way, but we do. So, okay, so here's how I could write this out. So there you go. So that's a way you could kind of simplify this. Okay, so moving on to 15 here. So this one is now going to break into the chain rule. And I have lots of videos where I break down how to actually use the chain rule. So we've got kind of two functions here where we're going to have to use this. So notice, starting with sine of 6x. So the thing to keep in mind here is our trig derivatives, they're just for sine of x. They are not for sine of 6x. So I have to identify then my outside function and my inside function. So my outer function would be sine, and my inner function in this case would be 6. And then for this other function, so my outer function would be e to the x, and my inner function would be 7x. So I'll color code all of that as we take the derivative. Okay, so I always like to work like from the outside in. So taking the derivative of the outside function here, the derivative of sine is cosine, and you leave the inside function intact, but then you multiply that by the derivative of the inside function, which would just be 6, okay? All right, and then moving on to the next derivative. So now I take the derivative of the outside function, which is e. So the derivative of e is just e, so this will just be e to the 7x. I leave that inside function intact. and then I multiply that by the derivative of the inside function. The derivative of 7x is just 7. So there's all the pieces for this one. So I've got f prime of x now is going to be 6 cosine of 6x minus 7e to the 7x. And this is kind of one of your standard chain rule problems, so you can look up more problems like that if you had problems with that. Okay, so for 16, so we've got more chain rule, we've got trig derivatives, and we've got quotient rule in here. So just to kind of briefly remind you, I like to show these real quick. So I'm going to be using the quotient rule here, and then this is my list of trig derivatives, so if you need to pause the video for either one of those, feel free. So I also need to know my outside functions and my inside functions. So for sine, my outermost function is sine of x, and my innermost function is 5x. And then for tangent of 2x, my outermost function is tangent of x, and my innermost function is 2x. So we'll just keep that in mind. All right, so to take the derivative, the way that this works is first I take the derivative of the top function. And in taking the derivative of the top function, I'm going to have to use the chain rule. So I take the derivative of the outside function, so the derivative of sine is cosine, and I leave the inside function intact. And then I multiply that by the derivative of the inside function. So the derivative of the inside function would just be 5. Okay, but don't forget, then you multiply all of that by the denominator function. Okay, there's the first part of this. I can already tell I'm going to run out of room, so I'm just going to continue on this line here. So now I leave sine of 5x. I leave the top function alone, and I have to take the derivative of the bottom function. So using the chain rule for this part, the derivative of tangent is secant squared, and I leave that inside function intact, but now I multiply that by the derivative of the inside function. The derivative of 2x is 2. And then all of this whole mess, is divided by the bottom function, and I will square it. Okay. So how do I make this look nicer? Well, one thing I can do is I can break this up. So let's see. I'm going to break this up into 2 separate fractions so that I can cross something out here. So there's the first part. So that was the first part of this. And now for the second part of this, I'm going to minus this whole thing over the denominator. So I'm just breaking it into 2 pieces. So it'll be minus 2 sine of 5x secant squared 2x, all of that over tangent of 2x squared. Okay, so let me make just a little space. And so now, let's see, I can cancel out one of these tangent, oops, I wrote tangent of 5x here. This should have been tangent of 2x, my bad. Let me fix that. Okay, I changed that to a 2. Sorry about that. Okay, so I can cancel one of these out with the denominator. So now, if I just want to make this look nice, the final answer here would be 5 cosine of 5x over tangent of 2x. And then I've got this other part here, which I can't really simplify any farther. But that would be as far as you can really go with your simplification. Okay, so moving on to 17 here. So this is really like a basic derivative rule. I don't know that all calc classes will cover inverse trig functions, but the class I teach does right now, so that's why I put it on here. So this is just really checking that you know the rule. So if you need a quick review of those, I've got the list here. So here's one set of your inverse trig derivatives, and here's the other list. So you can pause the video and check those out if you want. They're very similar. I have a whole video where I break down why these are what they are. So the derivative here then, it's really just knowing the rule. So this is going to be 1 over the square root of 1 minus x squared. And honestly, I know that there's like little conditions on this. I don't think it's important for you to write those down when you're actually writing down the derivative rules, though some teachers might want that, so it just kind of depends. Anyways, there's the derivative. So taking the derivative for number 18, we're going to need both the chain rule, and then I will just show you very quickly. So here are the derivatives of the inverse trig function. So if you need to pause the video, you can do that. So in this case, I need to recognize that I have this inverse tangent as an outside function and then 3x as an inside function. So to take the derivative of this, what I'm going to do is first I take the derivative of inverse tangent, which is going to be 1 over 1 plus, and then I want to square the inside function. So I just bring that 3x with, and then I multiply that by the derivative of the inside function. The derivative of 3x is 3. And so then to simplify this, this just becomes 3 over 1 plus 9x squared. So for number 19, we've got log base 3x minus 2 to the x. So these are actually both requiring these derivative rules. So I've just got those there. If you want to pause it, you can pause it. So these are just the standard derivative rules, really. So for log base 3 of x, that's going to be 1 over x times the natural log of 3. And then for 2 to the x, that's going to be 2 to the x times the natural log of 2. So that's just like the straight up kind of basic derivative rule, really. So for 20, what we have here now are we're using the chain rule for log base 5 of 4x and log of, or natural log of 5x. So here's just a quick cheat sheet of those derivatives. If you need that, you can pause and write those down. So for 20, what I want to recognize here, so log base 5 is my outer function, 4x is my inner function, and then the natural log is my outer function, and 5x is my inner function. So for this one, I'm going to take the derivative of the outside function. So the derivative of the outside function, I guess I'll color code it in this case. So this will be 1 over 4x times the natural log of 5. So notice I brought the inside function and I put it in the x position. And then I have to multiply this by the derivative of 4x, which is just 4. And then for the other one, so the derivative of the natural log is going to be 1 over x. But in this case, I keep the, instead of it being x, it'll be 1 over 5x. So I keep that inside function intact. And then I multiply that by the derivative of the inside function, which is 5. And so what I'm going to get is 4 over 4x times the natural log of 5 plus 5 over 5x. And then you can see that you can make some cancellations here. So at the end of the day, interestingly enough, I get 1 over x times the natural log of 5 plus 1 over x. So that would be my derivative. So for E here, so we're still using the chain rule. We're using our natural log, or sorry, our natural exponent and our trig rules. So the outer function here is E, and the innermost function is sine of x. So to use the chain rule here, I take the derivative of the outermost function, which would just be e to the x, but instead of it being e to the x, now it's going to be e to the sine x. And I multiply that by the derivative of the inside function. The derivative of sine x is cosine x. And so that would be it for this one. That is the derivative. Okay, so for 22 here, I'm using the chain rule, and I need to know my inverse trig derivatives. So here is just a quick cheat sheet. You can pause the video if you need to write any of these down. So I need my inverse cosecant right here. So wherever there's an x, I'm going to replace it with the inside function. So in this case, here's my outer function. 5x is my inner function. So what I'm going to do then is I'm going to have, let's see, 1 over, let's see, that's actually negative 1 over, and then this will be 5x times the square root of 5x squared minus 1. So let's see, make sure I get all of that there. Okay, so all of that is, that's all good. And then I'm going to multiply that by the derivative of the inside function. The derivative of just 5x we know is just 5. Okay, so now we have to simplify a few things here. So to simplify this, I'm going to have 5 over the absolute value of 5x, and then this will be 25x squared minus 1. Now, one thing that we can do, we actually can cancel out the 5's, because what is the absolute value of 5? Like this value is not going to change. So then I can just take this one step farther. Oops, I forgot the negative here, sorry. So this will be negative 1 over the absolute value of x times the square root of 25x squared minus 1. Okay, for 23 here, so what I have is really like the chain rule. I've got 3 functions here. So this is an outer function. This e function is like a middle function, and then I have this function here. So this is the innermost function. So just in case you need a reminder, sometimes people forget, the derivative for 2 to the x falls in this format here. And then I'm assuming that you know the derivatives of e to the x and 3 to the x if you're watching this. So, okay. So what I want to do here to take the derivative is first I take the derivative of the outermost function. So just remember, so that's gonna fall in the format of 2. Now normally it would be 2 to the x, but since this case we don't have x, we have all this other inner stuff. I'm just gonna bring all that inner stuff with, and then multiply that by the natural log of 2. Okay. Then next, I'm going to take the derivative of the next function, so e to the x, except it's e to the 3x. So the derivative of just e to the x would be e to the x. So this will be e, and then I leave that inner function intact. And then finally, I take the derivative of the innermost function, which would just be 3. And so my final answer in this case will be 3, let's see, e to the 3x times 2 e to the 3x times the natural log of 2. There's like, whatever order you want to write this in is totally up to you, but those are all the pieces that go with this. For the next problems, what we're going to do is we want to find the equation of the tangent line at the given point. So for this first one, so this is a really standard problem. This is a really great way to check if you really understand the derivative, because the derivative is not just taking these formulas. It really comes down to like understanding what happens at a tangent line. So for this process, what you're going to do is you're going to first, of course, take a derivative. This is calculus. We're in the derivative section. So the derivative of this function is 6x, but now where do you go from here? So what you want to do is you want to use this point. So notice if I were to plug this in, this would be a point off of this function. The only thing I need from this particular point, I only need the x coordinate. So I need to know what is the slope of the tangent line at this point. Well, like I said, we just need the x coordinate, and I literally just plug that x coordinate into my function. So if I take f prime of 1, that's going to be 6 times 1. So this is actually my slope of the tangent line. And then you have a point, right? You have a point and you have a slope. So when you have a point, boom, and you have a slope, that determines a line. So from here, I use the point slope form, that y minus y1 equals m times x minus x1. So I use all of that. So I'm going to plug in my point now and my slope. And then I can just go ahead and rewrite this in slope-intercept form. So this is going to be, let's see, y minus 1 equals 6x minus 6. And then if I add that 1 to the other side, I get 6x minus 5. So there's the tangent line. Okay, so for this one, so I still want to find the equation of the tangent line at the given point. So first things first, I have to take the derivative. So I have to use the chain rule here. So this will be cosine of 3x times 3. So that's 3 cosine of 3x. So next, I need to know the slope of the tangent line. And so to do that, what you're going to do is you really just need the x coordinate from this point right now to do that. So if I take g prime of 0, this is going to give me 3 times cosine of 3 times 0. So cosine of 0 is just 1, right? So this will just be 3. And so this is my m, it's the slope of my tangent line. So now I've got a point and I've got a slope. So I can use the point slope form, which I've written down here. And I can just plug all that information in now. So I'm going to have y minus 0 equals 3 times x minus 0. And you can see from simplifying this, so we get the equation y equals 3x. So that would be your tangent line. Okay, so for this last one, so I still want to find the equation of the tangent line at the point. So first things first, I've got to take a derivative. So the derivative of this will be 2x times the natural log of 2. So that's kind of a nastier looking derivative in some ways, but the process is the same as it always is. So to get to the slope of the tangent line, what I need to do is I need to use the x coordinate that I was given here. So if I plug that in, y prime of 2, well, what is that? That gives me 2 squared times the natural log of 2, so this is 4 times the natural log of 2. So don't get too upset about the fact that this is something weird. Just kind of go with it. This is ultimately a number, right? We don't know what the decimal value of it is, but it is just a number. And so this is really my m now. So I've got my slope, I've got my point, so I can just plug all of this into the point slope form. So it's always the same stuff, even if it's just, you know, kind of nastier looking slopes or whatever. So if I plug all of this in, I get y minus 4 equals 4 times the natural log of 2 times x minus 2. And so if I want to try to put this into slope-intercept form, so this isn't going to look too beautiful, but the way this will look, I'll have y minus 4 equals 4 times the natural log of 2x minus. So notice as I distribute this, so one thing I want to point out here, I can multiply 4 times 2. So that'll become 8 times the natural log of 2. And so then to finish this, my final line would be 4 times the natural log of 2x minus 8 times the natural log of 2 plus 4. And that's really as good as you can do here. So you'll have just some weird decimals otherwise. And so there you go. Okay guys, so that covers everything in this video. I'm super curious to know if you are using this to study, if you find that it's helpful. So always feel free to leave me comments with some feedback, or like or subscribe to the channel. Otherwise, thanks for watching. I'll catch you next.